Welcome to episode 2 of the Euler project, a series in which we solve the problems in the online Euler project using closure and then take them to the max. Problem 2 is a nice simple little ditty with a built-in trap. Find the sum of all the even Fibonacci numbers up to but not including 4 million. Fibonacci was an Italian mathematician who, while studying the breeding habits of rabbits, uncovered the mathematical sequence that now bears his name, the Fibonacci sequence. The sequence begins with 2 ones, and then every number thereafter is just the sum of the previous 2. So, 2 is 1 plus 1, and 3 is 2 plus 1, and 5 is 3 plus 2, and so on. So what we need to do is find all the even Fibonacci numbers up to 4 million, and then add them all up. That should be simple, huh? So to calculate a Fibonacci number is probably not very difficult. A simple recursive algorithm like this should work just fine. We're going to define a function here, Fibonacci, fib, which takes n. That's going to ask us to calculate the nth Fibonacci number. If n is less than 2, well, the answer is 1, because the first 2 Fibonacci numbers are 1. And then the Fibonacci number of n is just the sum of fib of n minus 2 and fib of n minus 1. So that's Fibonacci, right? So, okay, let's try this out. I've got a little REPL down here, and we say fib of 1 should be a 1. It is. And, fib of 2, that's, yep. Ooh, what's fib of 2? Oh, yes, because fib of 0. Yeah, because it starts at 0. Good, okay. Well, what's fib of 3? Fib of 3 is 3. Okay, and fib of 4, that should be what? 5, right? Yeah. So this looks like it's working. Now, let's do this for x in range 20. Let's get the first 20 Fibonacci numbers here. Fib of x. There we go. And this should create a list of all the Fibonacci numbers under 20. Up to Fibonacci number 20. So this is working. Okay, well, that was pretty easy. I guess all we need to do now is find all the Fibonacci numbers up to 4 million and take away all the odd ones and add up the even ones. I think we'd be done. So maybe what we should do now is find the first Fibonacci number that's greater than 4 million. So we should be able to solve this by inspection. Let's just do fib of 30, right? See, yeah, that's about 1 million. So fib of 31 is about 2 million, and fib of 33 is going to be 4. See, okay. So it's just the first 31, right? So, all right, let's do this. Let's say we want, let's define our fibs as for x in the range of, okay, I want 32, so in the range of 33. So it'll go from 0 to 32. That's what that's going to do. Fib of x. Okay, so that'll be our list. Good. And, the fibs are, took a while to print that, didn't it? But okay, that's that. Those are all. Now, let's get the even ones. So, def even fibs is going to be filter even fibs, right? Yes. Okay, good. And now we should be able to type even fibs. Right. Oh, isn't that nice? Okay, and that is, yeah, 4 million. There aren't that many of them, are there? It's just a few, and then reduce plus even fibs, right? Well, there's the number. Okay, 4613732. Let's take that number and we'll just stick it in the Euler thing here. So, problem 2. Let me bring it over so that you can see it. Yeah, okay. Yep, 4613732. Is that what we got? 4613732. Yep, that's the right answer. Okay. Hey guys, we're done. Ho 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 ho. Huh. But this isn't very satisfying, is it? I mean, we haven't actually written a program to solve the problem. We just kind of solved it through inspection. So let's write that program right now. So here's a little program that really should do this. Sum the even fibs up to some number. So we're going to loop starting at 0 and starting with an empty list. And we're going to let fib I be the fib of I, which will start out at 0. And if fib I is greater than n, well, we're done. So then we just add up the even fibs. Otherwise, we're going to loop back with the next I and add fib I to the list. So real simple, real easy. And this should work. Some even fibs up to 4 million should give us our answer, right? Is that 4 million? Yeah, that's 4 million. And that should give us our answer. And our answer is 4613732. Yes, okay, that's great. So I wonder what it is up to like 5 million. Let's find out. Let's find out what it is up to 5 million. Yeah. Okay. Okay. That was weird. Why is it the same? It's the same because the next Fibonacci number is greater than 5 million. Well, okay. Let's find out what it is up to 10 million. That ought to give us a new number. Seems to be taking a while. Okay. Oh, heavens. It's the same number. Is that right? Why would that be right? Let's try another number, like 20 million. Okay. Does seem to be running for a very long time, doesn't it? Oh, that's a different number. Okay, 1954484. What is that? 19 million? That's the sum. Yeah, that's the sum. Okay. Let's try it up to 100 million. Let's do that. Let's say 100 million. Is that 100 million? Yeah, that's 100 million. Okay. Okay. Does seem to be taking it a while. That number's only 5 times bigger, and the Fibonacci number should get up to 100 million pretty quickly. So, all right. My goodness, that's taking a very long time. I mean, heavens. Okay, we made it. 82 million. Well, I don't think I want to try 200 million. Why is this taking so long? If you think this is slow because we're constantly recalculating the same Fibonacci numbers over and over, you're right. Although you might not be right for the right reasons. If you thought the problem was in here, well, then you're mistaken. Oh, don't get me wrong, this is plenty inefficient. But there's a much bigger inefficiency. The real problem is this algorithm right here. This algorithm is terribly inefficient. And I can demonstrate that pretty easily. I can calculate the 20th Fibonacci number. We did that before. It seems to come out pretty fast, doesn't it? And the 30th, well, that comes out with a tiny little pause. And the 40th, I mean,
one's just going to take it a little while, isn't it? And as you can see, this is not a linear kind of issue. Now, I'm going to let it finish here because it'll finish in a second or two, or maybe 12. There we go. Here, let's demonstrate why this is happening, which we should be able to do right here by saying, oh, how about this? Pern fib of n. Yeah, let's give that a shot and see what it does. I wonder if this is going to work. Okay, let's see. I'm probably going to need to do a refresh. Okay. Fib of 1. Oh, yeah, fib 1. Okay, well, fib of 2. Oh, yeah, look, fib 2, 0, and 1. Fib of 3. Oh, yes, 3, 1, 2, 0, and 1. You can see that it's definitely calculating some of them over again. Fib of 4. Ooh, heavens. Let's see. Well, it did 4, and then 2, and then 0, and then 1, and then 3, and then 1, and then 2, and then 0, and then 1. And my goodness, it starts to do a lot of them. Let's try fib of 10. Let's see. Okay. Fib of 10 is 89, and oh, well, you can see that there's actually quite a few of them getting done over and over and over and over, over and 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 over. Oh, yes, okay, so it's going to take an awful long time if we want to do, say, fib of, well, let's just try 15. Yeah. How big is that one? Well, I'm just going to scroll that one. And yeah, it's pretty big, isn't it? It just keeps on going and going and going and going and going. I don't need to belabor this point. You get the idea. We're going to have to do something to speed up that algorithm first, because that's the real slow one. One way to speed this up is to use the trick of memoization. Memoization is just the idea that we will remember the result from every function call so that we don't have to recalculate it every time. Closure gives us a nice little function called memoize, which will take any function and convert it into a function that remembers its own answers. So here's the memoized version of fib, and if you look closely, you'll see that that little bit right there is the original Fibonacci algorithm, right? So, except that it's now cast as an anonymous function that is fed into memoize and then given the name fib. So that recursion actually recurs back to the memoized function. Interesting. And I can demonstrate this. And, fib of 1 is, 1, and fib of 10 is 89, and fib of 40, that was the slow one, right? Well, that's really fast now, right? And fib of 50 is it's getting up there, but you'll notice that it's no longer slow. The memoizing seems to have solved that problem, and in fact, we can do the sum of even fibs up to 100 million. And that should not take a long time. And maybe we could even do it up to 200 million. Remember, I didn't want to do this before. Oh, yeah, well, of course, it didn't change anything because it wasn't another even fib. But let's make it, 400 million. And, oh, yes, we see it's very fast now. So the problem was the inner algorithm, even though this part here is still pretty inefficient. The real problem is in here. Now that's been resolved at the expense of a little extra memory. That extra memory hasn't hurt us very much so far because we really haven't gone past maybe the first 50 Fibonacci numbers. Turns out that Fibonacci numbers get really big really quickly. But what if we didn't want to waste all that memory, right? I mean, what if we were going to be calculating really, really huge Fibonacci numbers and we didn't want to load up that big memoized table? Maybe in that case, what we should do is use iteration.
Iteration enclosure is just tail call recursion. We just make sure that the very last expression in a function is the call back to that function. Or if we want to save stack space, the call to recur.
So here's the iterative version of the fib function. And you see that I've used this overloading form here where I've got two different signatures for arguments. The original one is just this one. This is the version that calculates the Fibonacci number n, right? The nth Fibonacci number. And if n is less than 2, we're going to return 1. If it's not less than 2, then we are going to call fib, which is this function here, with n minus 1 and 2 1s, right? So here is the overloaded version, which takes 3 arguments. That's what this one is going to call. And if n is 0, then we're done, and we simply return b. That may confuse you, but it'll become clear in a moment. If n is not 0, well, then we are going to recur, decrementing n, and putting b in the place of a, and a plus b in the place of b. Now, you can stare at that for a little while and convince yourself that it's right, but I can demonstrate it down here and show you that it is right. So, here, let's do this. Let's do that great for loop. The first 10 Fibonacci numbers, there you go. All right, pretty good. And I can also say, fib of 60, and that's our old familiar 250 million or whatever that is. What is that? That's, 2.5 billion. And you notice it came out really fast, right? And of course, we can do the sum of the even fibs up to 400 million. It's fine. And that's going to be really fast, too. So instead of memoizing here, what we've done is to iterate. And that's really fast, too.
So now let's look at the function that actually solves the Euler problem here. And you look at it, you'll see that it's got some efficiency problems. Recalculates the Fibonacci numbers over and over again. Now, when we were using the memoized fib, that really didn't matter so much. But now that we're using the iterative fib, well, all that recalculation is kind of wasteful. So maybe what we should do instead is use iteration, but use it to calculate the entire list of Fibonacci numbers, at least up to what we want.
So I've changed things around a little bit here. I've created this new function called fibs. And what fibs does is it returns a list of Fibonacci numbers up to n. That's what this part of the function does here, this particular overload. You pass in how many Fibonacci numbers you want, and then it calls the first overload here, this one here, right? And it says, okay, well, we're going to start with a 0 and a 1, and the number you want, and an empty list. And then it does the standard kind of looping around here. And, this could be fibs or this could be recur. It doesn't really matter, but, fine. We're not going to be looping that many times. It builds up the list of Fibonacci numbers. And you kind of recognize this from the previous iteration, and that shouldn't be too surprising there. And then, of course, what we're doing is we're adding the next Fibonacci number to the end of the list. Now, I can demonstrate this for you if you want to see it. And here's fibs 10. Let's get the first 10 Fibonacci numbers. And there they are. There they are there. And we could get more of them. We could get fibs of up to 50, for example. And okay, those are the Fibonacci numbers up to 50. They're pretty big. The second function here, up here, is the rewrite of the function that figures out the Euler problem. And frankly, very little has changed here, except that I created this this variable here, fs, or fibs, with all the Fibonacci numbers, with the first 90 of them, right? Which is more than enough to handle all all the stress that we've been putting it under. And the rest of it is pretty much the same, except that instead of calling fib I call nth fs I, which essentially gives me the same thing. So in some sense, the list is kind of the memoization, although now it's not automatic. It kind of happened explicitly. And other than that, it works normally. So I can come back here and I can show you, the sum of the even numbers up to, say, 400 million is our good old friend 350,704,366. Yeah. Okay. So this works and it's fast.
But my goodness, that magic number 90, that's kind of annoying, isn't it? And then there's the fact that we're using up all that memory. Okay, now I realize that it's not really that much memory that we're talking about here, but let's just say that we just don't want to waste any memory for whatever reason. We don't want to worry about memory. So how would we solve these two problems? One solution is to get lazy. Let's build a version of the fibs function that returns a lazy list instead of an instantiated list.
Okay, so here is the version of fibs that returns a lazy list. And the sum function just took the 90 out. so the 90 is gone. That's good. And look at the fibs function. It's much cleaner, isn't it? It's a lot smaller. And although you notice that it doesn't seem to have an exit criteria. I mean, it looks like an infinite loop, doesn't it? Well, let's just look to see if it is first. Here, let's do this. I'm going to take the first 10 of the fibs list. That seems to be working, doesn't it? Okay, well, let's do the summing business. There it is. We're going to do the first 400 million. And, oh, yeah, there's our regular old number there, 350,704,366. There it is. So that seems to be working. Let's take a look at this fibs function. And you got to read this a little bit backwards. You notice that it's using cons here. Remember in the previous one we used conj. Well, cons puts things at the front of the list, not at the back of the list, typically. It depends on whether it's a vector or not. But in this case, lazy lists are seeks, and cons adds to the front. And so if you look at that carefully, you'll realize that this is kind of working backwards, isn't it? Now, I'll let you stare at it, try and understand it. Of course, the key to it is this lovely function here, lazy seek, which does all the magic. But it does, in fact, create a list. Now, what's really remarkable about this is that when you call fibs here, this one here, it doesn't actually do any of the work. It just puts a marker in there, and that it's a lazy list. Then we kind of walk through that list one at a time. And as we do, we are calculating the next one in line, right? So we keep on incrementing I down here, and that means we're going to calculate the next one and the next one and the next one. And all those stay in memory because I'm holding the head of the fibs list here. So I'm not saving any memory here. I've just kind of gotten rid of that 90. I wonder if we could get rid of the memory too. The trick to getting rid of the extra memory in the lazy list is to avoid holding on to the head. Let me show you how to do that. All right, I haven't changed the fibs function at all. That's still the same, produces a nice lazy list. I have made significant changes to the sum even fibs up to function. And you could argue that this is the way it should have been written all along, but what fun would that have been? In any case, the summing function starts with a loop. And this time, we're going to initialize fs to be the lazy list. And we're going to initialize the sum to be a 0. Now, within the loop, we let fib be the first element of the lazy list. That's going to force one calculation to take place. Okay, if that calculation yields a fib, it will, then if that fib is greater than n, then we're done, and we might as well return the sum. But if it's not greater than n, then we are going to recur with the rest of s. So I'm not holding on to the head of fs. I'm going to just pass in the rest of fs, and the head gets dropped. That means that memory location is free to be garbage collected. Nobody will ever use it again. And if the fib is even, well, then we're going to add it to the sum here. But if it's not even, then we'll just reproduce the sum. So we're only adding the evens. Now I can demonstrate this, and let's do the sum of the even fibs up to 400 million. Yeah, and that should be our good old number. There it is, 350,704,366. So isn't that nice? And now I'd like to show you something, though. Take a look at this, right? If I define fs to be fibs, so now fs points to a lazy list that so far hasn't calculated anything. Now I should be able to say take 1 fs, right? And that should return a 1 because, well, because that's the first element of the list of Fibonacci numbers. And if I were to say take 10 fs, well, that should give me a list of the first 10 Fibonacci numbers. And if I were to say nth 20 fs, I think it's fs20, isn't it? fs20, yeah, that should give me the 20th Fibonacci number. So that's pretty good. And fs, let's say 80, that'll give me the 80th Fibonacci number, which pretty big number. And let's see, nth fs 89 is a pretty big number. Oh my goodness, that's a very large number. What number is that? That's let's see, millions, billions, trillions, quadrillions, quintillions. 2.8 quintillion. That's a pretty big number. And fs 90, and what's that one? Oh, the calculation took place at that moment, and it threw an integer overflow. So that proves that the calculation had not yet taken place until I went to fetch it. That's lazy lists. That's one of the issues of lazy lists, is that they can cause exceptions to occur when you kind of don't expect it. That last bit was kind of annoying, wasn't it? I mean, why are we limited to 2.8 quintillion? Now, what if we wanted to find sums of even larger Fibonacci numbers?
Use big integer.
Sure. I mean, it's pretty simple. All I did was add these n's onto the end of those ones right there. And gee, I think that's all I really have to do. And now I think if I say, here, and here, let me define fibs. Define fs as fibs. Good. Okay. Good. Yeah. Now let's say nth 90 fs, right? I think that's the way you do that. Oh, it's the other way around. Nth fs 90. I keep on forgetting which direction that is. Oh, there we go. Look. Yeah, that's like million, billion, trillion, quadrillion, 4.6 quintillion. Yeah, okay. All right. Well, I think I can probably do better than that. Let's do this. Let's do the sum of the even fibs up to 1 million, billion, trillion, quadrillion, quintillion, sextillion. Yeah. Okay. That was really fast too, wasn't it? Let's see, what is that? Yeah, well, I'm not going to count that up for you. Just, it's just not that hard to use big integer enclosure, guys.
Now, I don't know why you'd want to play with Fibonacci numbers that big, but this is the Euler Project series, and we take things to the max around here. So you want big fibs? You got big fibs. But before I go, there's one more thing I'd like to show you. What do you think happens if we put two consecutive Fibonacci numbers in ratio? Like fib 6 and fib 7.
Well, let's try it and find out. I've written this nice little ratio function, which takes an n, and first of all, we calculate the lazy list of Fibonacci numbers, and then we go ahead and we get the n plus 1th Fibonacci number and the nth Fibonacci number, and we put them in ratio to each other and return that as a nice floating point number. Now, let's see what this does. Let's say, ratio 1. Well, we know what that's going to be. That's going to be a 2, right? Because, okay, 1 to 2, yeah. And ratio 0 should just be a 1. Yeah, okay, all right. So ratio 3 is going to be, 1 2/3. Makes perfect sense. And ratio 4, that's going to be 1.6. And ratio 5, well, yeah, here. Let's do this. For x in the range of 20. Let's do ratio x. Good. Now that'll just do them all for us. And okay, yeah, we see them all here. And yeah. Nice. Sort of looks like it's converging, doesn't it? I mean, there's 1.61803334. Yeah. Okay. Looks like it converges. So ratio. Let's try ratio 30. Okay, let's try ratio 40. Yeah, they're real close to each other. How about ratio 50? Well, 50 and 40 are the same, so they've converged as far as our floating point resolution is concerned. Well, that's interesting. Now, here, let's define n to be ratio 50. That's going to be our converged number. Okay, all right. That seems to be interesting. Now let's do let's say 1 over n, right? Let's divide n into 1, and that's interesting, isn't it? It's the same fraction, just minus 1. Let's try this times n. Interesting. It is the same fraction, just plus 1. N happens to be a very interesting number. A number called phi. A number that you and I are going to explore in part 2 of the Fibonacci problem.
Well, that was interesting. I think we had some kind of a weird power failure there or something. Anyway, you guys aren't going to want to miss the next exciting episode of Euler Problem 2, Part 2. Turtles all the way down.